Today we're diving deep into the fascinating world of double emulsions and core shell droplets. These are sophisticated structures that enable us to encapsulate drugs, cells, or reagents in nested compartments by controlling multiple interfaces. Let's start with the basics. What exactly is an emulsion? An emulsion is a dispersion of one liquid in another immiscible liquid. Think of oil droplets suspended in water, or water droplets suspended in oil. Here we see oil droplets dispersed in a continuous water phase. This is called an oil and water emulsion, or O/W for short. These emulsions are stabilized by surfactant molecules that sit at the oil-water interface, reducing interfacial tension and preventing coalescence. Now let's talk about double emulsions. What makes them special? A double emulsion is literally droplets within droplets. It's a hierarchical structure with nested compartments. This is a water in oil in water double emulsion, written as W/O/W. We have inner water droplets surrounded by an oil shell, all suspended in an outer water phase. There are two main types: water in oil in water, which we just saw, and oil and water in oil, where you have oil cores inside water shells inside an oil continuous phase. Now you might ask, why do we need such complex structures? What problem are we solving? The key challenge is protecting sensitive cargo from the external environment. Many drugs, proteins, or cells are water-soluble but need to be delivered through hydrophobic barriers or protected from degradation. Consider insulin delivery. Insulin is a water-soluble protein that degrades in the stomach. We need to encapsulate it in the inner aqueous core, protect it with an oil shell, and release it in the intestine. The real power of double emulsions comes from controlling multiple interfaces. Let's understand why this matters. Each interface provides a physical barrier and a control point. The inner interface controls what enters the core, the outer interface controls what leaves the shell. Interface 1 controls entry into the core. Interface 2 controls exit from the entire droplet. By tuning surfactants and compositions at each interface, we achieve precise control over permeability and stability. Let's do a quick back-of-the-envelope calculation. What are typical sizes for these structures? Outer droplet diameters typically range from 100 to 500 micrometers. Inner droplet diameters are usually 10 to 50 micrometers, about 10 times smaller than the outer droplet. The oil shell thickness is typically 20 to 100 micrometers, providing substantial protection for the core. Let's calculate how much drug we can encapsulate. Suppose we have an outer droplet of 200 micrometers diameter. The outer volume is 4/3 pi r cubed, where r is 100 micrometers. This gives us 4.19 times 10 to the 6th cubic micrometers, or about 4.2 nanoliters. If the inner water cores occupy about 30% of the total volume, which is typical for well-formed double emulsions, the total core volume is 1.26 nanoliters. This is the volume available for drug loading. Now let's calculate actual drug loading. Suppose we want to encapsulate a protein drug at 10 milligrams per milliliter concentration. 10 milligrams per milliliter equals 10 micrograms per microliter. The mass of drug per droplet is concentration times volume. 10 micrograms per microliter times 1.26 times 10 to the minus 3 microliters equals 0.0126 micrograms, or 12.6 nanograms per droplet. If we have 1 milliliter of emulsion containing approximately 1 million droplets, the total drug loading is 12.6 nanograms times 1 million equals 12.6 milligrams. That's a substantial therapeutic dose in just 1 milliliter. How do we actually make these complex structures? The answer is microfluidics. In a microfluidic device, we have 3 coaxial channels. The innermost injects the core aqueous phase, the middle channel provides the oil phase, and the outermost channel supplies the continuous aqueous phase. Precise flow rate control generates monodisperse double emulsions. The key to success is controlling flow rate ratios. Let me explain. We define flow rates as Q inner for the core, Q middle for the shell, and Q outer for the continuous phase. A typical ratio might be 1 to 3 to 10. For example, if Q inner is 100 microliters per hour, Q middle is 300 and Q outer is 1000. The shell thickness is primarily controlled by the ratio of Q middle to Q inner. Higher Q middle gives thicker shells, providing better protection. There's an important dimensionless number that governs droplet formation, the capillary number. The capillary number equals mu u over gamma, where mu is the dynamic viscosity, u is the characteristic velocity, and gamma is the interfacial tension. The capillary number compares viscous forces that want to deform the interface to interfacial tension forces that want to keep it spherical. When the capillary number is less than 0.01, we're in the dripping regime, where individual droplets pinch off regularly. When the capillary number exceeds 1, we enter the jetting regime, where a continuous jet forms and breaks up chaotically. We want to stay in the dripping regime for monodisperse droplets. Let's explore a concrete application: oral drug delivery of protein therapeutics. The problem is that protein drugs like insulin or antibodies are rapidly degraded by stomach acid and digestive enzymes. We encapsulate the protein in a W/O/W double emulsion. The oil shell protects it through the acidic stomach. When it reaches the neutral pH intestine, we engineer the outer interface to destabilize and release the drug. We use pH-responsive surfactants at the outer interface. At pH 2, they're stable, but at pH 7, they change conformation, destabilizing the emulsion and releasing the protein payload. A critical parameter is encapsulation efficiency. How much of our drug actually ends up inside the cores? Encapsulation efficiency equals the concentration of encapsulated drug divided by initial drug concentration times 100%. For well-optimized double emulsions, encapsulation efficiencies typically range from 60 to 90%. Some drug remains in the oil phase or outer aqueous phase. You might ask, what limits the encapsulation efficiency? Why can't we get 100%? The answer involves two phenomena. First, some molecules partition into the oil phase based on their hydrophobicity. Second, many drugs and proteins adsorb to interfaces, getting trapped at the oil-water boundaries rather than staying in the aqueous core. Another powerful application is encapsulating living cells. This is revolutionary for tissue engineering and cell therapy. We encapsulate cells in aqueous cores containing growth medium. The biocompatible oil shell allows oxygen and nutrient diffusion, while protecting cells from shear stress and immune recognition. Remarkably, cells can remain viable and even proliferate inside these droplets for weeks. The key is choosing biocompatible oils and maintaining proper oxygen transport. Let's calculate if oxygen diffusion is sufficient. This is a critical design constraint. The diffusive flux J equals -d times dC dx, where d is the diffusion coefficient and dC dx is the concentration gradient. The oxygen diffusion coefficient in oil is approximately 10 to the minus 9 meters squared per second. For a 50 micrometer thick oil shell, the diffusion time equals L squared over 2D, which is 50 micrometers squared divided by 2 times 10 to the minus 9, giving 1.25 seconds. This is fast enough to supply oxygen to cells. A typical mammalian cell consumes about 10 to the minus 17 moles per second of oxygen. If we have 10 cells per droplet, we need 10 to the minus 16 moles per second oxygen flux. Our calculation shows diffusion easily supplies this rate. Now let's discuss core shell droplets, which are simpler than full double emulsions but still very useful. A core shell droplet has a single core centered in the shell, rather than multiple dispersed cores. This provides a cleaner structure with a single continuous core. Core shell droplets are easier to fabricate because you only need 2 coaxial streams instead of 3. The core naturally centers due to interfacial tension minimization. An exciting variation is Janus droplets, named after the two-faced Roman god. Janus droplets have 2 distinct hemispheres with different properties. One side might be hydrophilic, the other hydrophobic. This asymmetry enables directional drug release or self-propulsion. Let's dive deeper into the physics. Interfacial tension is the driving force for stability or instability. Interfacial tension gamma is the energy per unit area at the interface, typically measured in millinewtons per meter. For oil-water interfaces, gamma is typically 20 to 50 millinewtons per meter. Surfactants reduce interfacial tension by factors of 10 to 100, stabilizing the emulsion by reducing the energy cost of creating interface. There's a pressure difference across a curved interface called the Laplace pressure. The pressure difference equals gamma times the sum of the reciprocals of the two principal radii of curvature. For a sphere, this simplifies to 2 gamma over r. Let's calculate for a 50 micrometer radius droplet with 30 millinewton per meter interfacial tension. The Laplace pressure equals 2 times 0.03 divided by 50 micrometers, giving 1200 pascals, or about 1% of atmospheric pressure. This pressure difference drives Ostwald ripening, where small droplets shrink and large droplets grow over time, because molecules diffuse from high-pressure small droplets to low-pressure large droplets. An important design question: should we use multiple small cores or one large core? Multi-core designs have many small droplets dispersed in the shell. Single core has one large centered droplet. Multi-core provides higher interfacial area between core and shell, which can accelerate drug release through the interface. Single core is more stable because there's no risk of internal droplets coalescing. It's also easier to control the core position. Let's quantify the interfacial area difference. For a single core of radius r, the surface area is 4 pi r squared. If we split that same volume into n smaller droplets, the total surface area becomes 4 pi r squared times n to the 1/3 power. The ratio is n to the 1/3. For 10 droplets, surface area increases by 2.15 times. For 100 droplets, by 4.64 times. Double emulsions are powerful for controlling chemical reactions in isolated compartments. We can encapsulate different reagents in separate droplet populations. Initially, they're isolated and can't react. We trigger the reaction by inducing droplet coalescence or rupturing the shells, allowing reagents to mix only when and where we want. This enables high-throughput screening where each droplet is an isolated microreactor. We can screen millions of reaction conditions in parallel using tiny volumes. Understanding release kinetics is crucial for drug delivery applications. For first-order release, dm/dt equals negative km, where m is the remaining drug mass and k is the release rate constant. This gives exponential release. m of t equals m0e to the negative kt. The half-life equals natural log of 2 divided by k. The release rate constant k is inversely proportional to shell thickness. Thicker shells give slower, more sustained release. If we want a 6-hour half-life, k equals natural log of 2 divided by 6 hours, which is 0.116 per hour. How do we achieve this rate constant? We tune the shell thickness and permeability. The answer involves choosing appropriate shell thickness and surfactants. A thicker shell or less permeable oil phase decreases K, extending the half-life. We can go even further with triple emulsions, adding another layer of complexity. This is a water in oil, in water emulsion. 5 phases alternating between aqueous and oil. Each interface provides additional control over encapsulation and release. Triple emulsions enable sequential release of multiple drugs from different compartments with different release kinetics. One challenge with all these structures is long-term stability. What causes them to fail? Coalescence occurs when droplets merge together, destroying the compartmentalization. This happens when surfactant coverage is insufficient. Ostwald ripening causes the size distribution to broaden over time as molecules diffuse from small to large droplets due to Laplace pressure differences. Creaming or sedimentation occurs due to density differences. Droplets float or sink based on whether they're lighter or heavier than the continuous phase. How do we combat these instabilities? Using high surfactant concentrations creates dense packing at interfaces, providing electrostatic and steric barriers against coalescence. Adding polymers that form gel-like shells provides mechanical reinforcement, creating a solid-like barrier that dramatically improves stability. Carefully matching the density of the droplet to the continuous phase prevents gravitational separation. This requires tuning the oil and aqueous phase compositions. Let's examine a real-world application: vaccine delivery using double emulsions. The protein antigen is encapsulated in the aqueous core, while an immunostimulatory adjuvant is dissolved in the oil shell. This co-localizes both components. After injection, the emulsion slowly releases antigen, providing sustained stimulation of the immune system over weeks. The adjuvant enhances the immune response. This provides sustained release over weeks to months, eliminating the need for booster shots and improving immune memory formation. Let me summarize the key principles we've covered. Multiple interfaces provide precise control over encapsulation, protection, and release of sensitive cargo. The structure is determined by flow rate ratios in microfluidic devices and by interfacial tension between phases. Shell thickness is the primary parameter controlling permeability and release kinetics, with thicker shells providing slower release. Applications span from oral drug delivery and cell encapsulation to chemical microreactors and vaccine delivery. Successful design requires balancing long-term stability against the desired functionality, often involving trade-offs between protection and release rate. Looking forward, what are the emerging directions? Stimuli-responsive materials enable on-demand release triggered by light, ultrasound, or changes in pH or temperature at the target site. Integration with 3D bioprinting allows printing of complex tissues with cells encapsulated in protective droplets during the printing process. Creating artificial cells with multiple nested compartments, mimicking organelles, enabling complex synthetic biology applications. Double emulsions and core shell droplets represent a powerful platform for compartmentalizing and protecting sensitive materials. By controlling multiple interfaces, we achieve unprecedented precision in encapsulation and release. The physics of interfacial tension, diffusion, and flow combine to create these remarkable structures. Whether delivering drugs, protecting cells, or enabling high-throughput chemistry, these nested compartments open new possibilities in biotechnology and medicine. The ability to engineer matter at the microscale with such precision is truly transformative for science and healthcare.